Okay, chapter 3 we started last Friday, but rather than doing 2.4, I give you something else which is really connected to the 2.4, the reflection of acoustic wave or shock wave. You can think either way. And something like for the conditions at the boundary between the two different media, which means important two media. So we are dealing with in the naval problem is what? Air and try open it. Anybody? Oh, so I thought we have a 10, then only 9. I think Willis. Okay. And the two media we are really dealing with is first, what's the two media? Air and water problem. That air-water interface is one type of the problem. Another type of the problem is water and rigid, like the sea bottom. And it's not really rigid. Some wave it absorb, but for the ideal situation is, let's say, the rigid bottom, which means everything is reflecting back. But in reality, some wave transmit right into the base or sea bottom. So once you know how to handle the rigid, then the other case is easy to handle. And another situation is some obstacle in the water. You wouldn't believe sea has a big, huge mountain in underneath. You heard about that, no? There is a mountain in the Tonghae East Sea, Yellow Sea, South Sea surrounding Korean peninsula. There are a heavy mountain in under the water, and it's very, very noisy water. And it's not like a calm. The West Yellow Sea is, as far as I know, is much noisier than the Tonghae, the East Sea. East, right? Yeah, East. Because Tonghae has almost has no mountain, but in the Yellow Sea, tremendous mountain, which means once a submarine dive into it, it's so noisy you can't find the submarine. It's gone in the noisy environment. You can't find it easily. And there are lots of, as a result, there are lots of obstacles. So it reflects back. So that's the kind of obstacle. But here we're gonna really virtually deal with, as I mentioned, air, water, rigid. That situation is what you're gonna handle. But another assumption, this is a very reasonable assumption for the shock analysis, okay? Like a motion of the water or gaseous product is described sufficiently well without the viscosity or other the dissipation mechanism. Shock wave is moved so fast, so damping doesn't wake up before at the moment the shock wave hit it. So usually that's what's happening. So you can neglect the viscosity effect of the water and also dissipation mechanism in the water or in the structures. So for the shock, I want you to think it's really extremely moving fast, like a wave, so you can easily think about that. Another condition at the boundary, there are two conditions at the boundary. When I say boundary, which is interface between the two media, okay? So here, there's mistakes here. What's the mistake here? Pressure is not the vector. Pressure is a scalar quantity. But I put the arrow, but it's not the accident. This look like pressure, but I'm just talking the pressure at the point very close to the boundary. Think that way, okay? And this P1 is the pointing right at the point near the boundary in media 1. This is for media 2. So when you consider the pressure right at the boundary, which is not at the point, but very infinitely close to the boundary, you can think P1 is equal to P2, okay? Pressure, scalar quantity. But what about the velocity quantity? Velocity quantity, of course, has the direction and the magnitude. So normal, this is a normal velocity right at the boundary in the media 2 and media 1 are same. Two different. So V1 is equal to the V2. So usually we're going to deal with the fluid particle velocity. You can deal with the wave, of course. This is a pretty general situations here. So that's very easy to say that. And now the reflection, now we're going to deal with the reflection wave right at the rigid boundary. So today's lecture and Friday morning lecture, I guarantee I'll give you a problem, exam problem, at least the first problem. I'm going to tell you as a part of the application, I'm going to give you the exam problem. So here, I mentioned to you Friday, this is rigid. This is rigid. And I'm going to draw, sometimes I draw the ray, the wave as an arrow. But sometimes I give you the wave as a plane wave or spherical wave front. So it doesn't make any difference. But for some explanation, drawing the wave front explains the physics better. So that's the reason. So I just give you both, okay? So this is like a plane wave. And this is rigid. Plane wave is moving in that direction with acoustic velocity c0, and this is alpha. Alpha could be any angle from 0 degree to 90 degree. If it's a 0 degree, what kind of the wave is this? Wave front is parallel to the rigid surface. If it's 90 degree, then it's really normal. Wave is really normal to the rigid surface, and there is no reflection wave for that. And no reflection wave at the rigid boundary. What does it mean? The pressure experienced by the rigid surface is same as the incident shock wave. No reflection. Any angle, okay, any alpha angle other than 90 degree gonna have the reflection wave, which means the rigid surface will experience the twice the pressure. Gusto, I'm glad you really keep coming to class, even if you take this course as an audit course. It's good. It's good. Usually they dropped after attending 2 to 3 classes. So keep coming in. It's going to help you eventually for your country. Okay, so of course this is a point, like I call this point as what did I do? Interaction point or intersection point? I forgot. Intersection or interact? I forgot what I said there. Intersection? Well, let's put intersection for the time being. That point, look at this. Then of course behind the wave, of course fluid particle, infinite number of fluid particles are behind there. Okay, and in front, and it could have a P naught, and of course it has a U naught in front before the shock wave hit it, right? Say yes, yes. And behind it is gonna be P and U all the way here. So as this wave hit it, then reflection wave will come down this way, right? As it hit it, it's gonna come down this way. So I'm gonna draw the reflection wave, which is coming down in the water, this water-free surface. This guy is coming down as a C naught also. But if you pay attention on here, this point, as wave is hit it, then reflection wave will come down this way, and this point is really moving zap this way, right? Along the boundary. Right? Yes. When it does that, first think this way, physics. Think this is called incident shock wave. Can you see Willie in the back there? Yes. Incident shock wave. And this guy is called the reflection or reflected shock wave. So I'm talking now here. This point, as this guy touches, as wave really move on with angle alpha, this angle, let's say alpha prime. In high school physics, we all know that. In high school physics, without sometimes proof, alpha is equal to alpha prime. No question asked, but we'll prove here using what rule? Snell's rule. Okay, so we'll see. So here, this point will, as this wave hit it, this point will move. As this wave move with the velocity of the c naught, this point, as you look at this incident shock wave, this will move pretty fast and along the boundary. I'm going to call that as C1, velocity as a C1, which is the shock wave velocity moving along the boundary as incident shock wave reach the boundary. At the same time, this guy, now concentrate on this guy, the reflected shock wave. As this guy move on, this wave will come down into the water as a reflected shock wave. And this point, which is kind of an intersection of this guy with the ridged boundary, this guy will move in C2 velocity. Okay, it's not the fluid particle velocity, it's a shock wave velocity. Okay, this point, which is intersection of incident and reflected wave, will move fast along the ridged boundary. So C1 is equal to, of course, the C2, right? Which is the point, intersecting point. So here, I'm going to say that C1 here is a C2, because it's right at the ridge, the boundary point. I'm going to set that as a point O. Pretty good. It's understandable. So now I'm going to look at this way. I'm going to just make this is 90 degree. I'm going to consider this triangle. Okay? Now look at me here. All this point here will, at the beginning, is going to hit it. Then this point will hit it. This point will hit it. All the point will hit it. So as I stand here, look along the boundary. This is C1. All that, let's say, the part of this wave, as it hit it along here, you can see that, just a wave zoom right there. Is this common sense? Is this C1 or C2? But when you consider incident shock wave, we're going to think C1. When you consider reflected wave, we'll consider C2. Quiz. Is C1 velocity, is it higher than C2? Lower than C2? I'm sorry. C1 higher than C0? Equal to C0? Or lower than C0? In other words, is it higher than C0? Equal to C0? Lower than C0? That's the question mark. Common sense first, then we'll look at that. Gusto, what do you think?
C1 is bigger.
Bigger. C1 is bigger than C0. One. What about Yongwon? Higher. Higher. How about Chorong Chongwon? It's a democratic society, so has to balance. Same. How about Zhongwen? This is bigger. How about Sunu? Same.
Everyone.
Oh, it's all. This is.
Larger than C.
Oh, okay. This is larger. Okay, no. Larger. How about the
Larger.
larger? How about the? Is it larger? C naught is bigger. This, right? C naught is incident. This is C naught is acoustic velocity in water. So for the wave, how about Sungwon? C1 is bigger. Willy's same. Who is the winner? And this is winner. Now this is so. It's 1, 2, 3, 4, 5, 6, 7, 7. This is only 2. This is only 1. So this is winner. My answer is I'm gonna agree with the winner because it's 7, 2, 1. Let's look at that. Now let's look at that. I'm gonna just erase this guy a little bit. So I said consider this triangle. Let's say as you consider this particular point in this triangle, let's say it takes a time t naught to arrive from here to here. The time it takes. Then the distance is going to be simply C naught times T naught, right? Right. This distance is like that. Before the math, this distance is longer or that distance is longer. From here to here, this distance is longer than this. Because this is, in this triangle, right triangle, this distance is the side, then which is longer than this or that. You agree with that, right? You agree with that, right? Yeah. And this is longer. But this, as you look at the wave, at the beginning, it's going to keep hitting. So I'm running from here to here, which this distance is longer. But as you consider, as this point hit that point, then this point, as you're zooming up, should hit that point at the same time. Which means the guy which stand right here and run, he should run faster to get down to this point at the same time, simply speaking. In other words, I'm going to call this is O, and this is A and B. Okay? This distance, OA, times what? Sine alpha is equal to AB, right? Make sense? And OA is C1 times what? Times T naught. It takes T naught time, then this point hit it here. as it really is. And sine alpha is equal to AB. AB is C naught. T naught. Make sense? And T naught can drop this. So C1 is equal to sine alpha C naught. Right? Sine alpha is smallest is starting from 0 down to 1, right? And as you consider this reflection wave, this reflection wave, this is 90 degrees, same thing, you can claim that. So I can say that C2 is equal to C naught sine alpha prime. Same token, exactly the same way. C1, C2 is the same. So C naught over sine alpha is equal to C naught sine alpha prime. So you can claim that alpha is equal to alpha prime. This is called Snell's law. I told you I'm going to include the problem set which you should apply the Snell's law for shock problem. Okay? It's interesting for the shock problem. So this is what I'm explaining here, and also fluid particle behind here I indicated as U. Okay, I indicated, I draw in the same line, but doesn't make any difference. If this is U, then I can draw, this is alpha, because this is alpha, then this is alpha. This guy plus that guy is 90 degrees, this guy, that guy, so this is alpha. And this velocity vector is of course U cosine alpha, which is normal to the rigid surface. Which is normal to the rigid surface. And as you consider this guy, which is, let's say, the U prime, it's U prime, and if you draw the normal component, which is what? This is U prime cosine alpha prime. Alpha prime is equal to alpha. This guy is U prime cosine alpha. So if I all along the wavefront, so now I'm going to draw this guy, which is coming down, which is U prime cosine alpha, which is same as alpha prime, and this guy is going up, right, for the incident shock wave, which is U cosine alpha. So if you look at that, what you claim is U cosine alpha prime. This is if you say coming down is negative, then this is going up is a positive, which is equal to U cosine alpha. So cosine alpha is same as cosine alpha prime. So you have a U prime is equal to U. So that's really true for right in the vicinity of the intersection point. That's our interest. what's happening when the wave, shock wave, hit the rigid surface. So you have a 2. For the rigid, u prime is equal to u, and alpha is equal to alpha prime. That's the reason. So here, this is behind the incident shock wave is P and U. In front is P naught and U naught. And for the reflection wave, or reflected wave, in front is, of course, P and U. Behind is, let's say, P prime, U prime. Then you can have wave relations as follow. This Snell's law is a general Snell's law. I'll hold until we discuss with air and water situation. So this is what I explained here. So now look at the slide there. Now it's very easy to explain now. This is still rigid boundary with the water. This is what wave? Incident shock wave. In front is P naught and U naught. Behind is P and U. And I talked to you, this is worth to remember. Plane wave or spherical wave, doesn't matter. P naught, U naught. Behind is P and U. Then shock wave equation, then we really did, is P minus P naught is equal to rho C U minus U naught, right? You all know that. So it's exactly what this is. It's no difference. Wave is happen to be put this way. Who cares? This way, who cares? So I said usually U naught is equal to 0. Two ways you can consider. That's what I explained the other day. So because in front of the shock wave, before explosion occurs, everything's all calm, beautiful horizon. You can sit back in the deck. You had a beautiful, nice dinner. Then bang! That's the explosion. So you can think U usually naught is equal to 0. And I say U naught is equal to 0. You can think of that too. Right at the boundary, usually this is the situations. We can, or sometimes I said P minus P naught, replace that as a P, as a dynamic pressure. Take out all the static component. So I said you can just consider P is equal to rho Cu. Don't confuse, nothing to confuse. Okay? So right at the boundary here, this is what I'm considering. And now considering the reflected shock wave, behind is a P prime. You can consider, this is a little bit tricky to understand, behind here, all the way down here. This is right around here. This is just took off, okay? If it's touched forever, U prime is equal to 0. Then it's distorted the thought you would have. It just infinite time, infinitely small time it took off. Okay, and in front, right here is in front. Here is U. Behind this U prime. Okay, don't misunderstand. It's just on the verge of took off. In front has been touched. Then in the verge of takeoff. So I can cast into this equation form U prime, which is behind the reflected wave. It just barely took off. And U is, think at the end of this guy is in front, is 0. So a little bit hard to understand. Is right at the interface. So you have P prime behind, P is in front. Then if you add these two together, you got that one. What does it mean? Twice of this guy. If you add these two, you have this or just this. Twice. This is really, you can interpret this guy as the pressure experienced at the rigid surface, which is twice of the incident shock wave. Remember, if it's rigid. But is there anything which can be perfectly rigid? No. It's always flexible. But if it's really stiffness is really hard, then you can think as a rigid. Okay. However, except the one situation, the wave is perpendicular to the rigid surface here. When alpha is 90 degree, then what happened? When alpha is 90 degree, there is no doubling effect. You have to exclude that situation. When alpha is 90 degree, is called the acoustic paradox. Mathematically okay. Practically or in engineering sense, there is no such a thing as a perfect alpha is 90 degree. Okay? Impossible in reality. Then the rigid surface will experience almost always what pressure? Twice the pressure. Okay? For practically rigid, when you have 1,000 megapascal the shock pressure, you can comfortably say in any situation it is 2,000 if it's rigid. Okay, because nobody is perfect. Understandable? This is a clue. So now this part, most difficult part, once you understand this, then that's very easy to understand for air-water interface. Now, this is a free surface. Then incident shock wave hit the free surface. And then right at the surface, reflection wave will come back straight down into the water. This is a interface point or intersection point. Interface point may be better. And this is alpha prime, we know is the same. But there is a wave which will transmit into the air. Air-water impedance ratio is about what? Rho C in water is how much higher than rho C in air? Li, wrong. Who cares?
1600.
Really? I don't remember. I don't memorize. Very good, but stupid. Why? Because this is very special case. Air, water, that's the situation. 3600, roughly, not exact, depend on temperature, it changes a little bit. Rho C is sometimes called just impedance or characteristic impedance, which is really showing the acoustic property of the water and air. So that tells big story as you learned already. The rho Cu, that's a pressure. Rho C, let's consider air. Rho C, very small compared with the water. Rho Cu, then pressure is very small, should be small. It's all the relative each other. So if you have 1,000 consequence first. If you have 1,000 megapascal pressure hit the free surface, almost zero pressure will escape into the air. In other words, when you conduct the testing, shock testing, we usually test for using those, well, it's a good sized pond, which is like old quarry. Old quarry, all the mines, all the days they digging for gold and coal, all that. Then after they really got chunk of really coals or good precious metals, then they abandon. Then what they do in U.S., they fill that with the water and use as explosion testing. Way deep in the countryside. Then we put the charge. I usually do as a school project something like a 60-pound HBX1 charge, which is about 50% stronger than TNT. And that's a Navy so-called shelf item. I can get it free of charge. But if you're going to make a TNT, small spherical charge of TNT, let's say 5 kilogram, to make about 10 of them, it costs about, nowadays way more, about $15,000. But 60 pounds is free. So Hassan, what you gonna do? You gonna take the free, or you gonna pay 15,000? You wanna take free. So that's what we did quite a bit. Anyway, remember, rho C, 3,600 times difference. God bless you. And this is escape into the air. And angle is, let's say, alpha double prime. And let's say CG is what? CG gonna be acoustic velocity in air, okay? And I'm gonna say that UG is fluid, the air particle velocity behind the shock wave, which escape or transmitted into the air. Got it? Yeah, got it. If you look at that point, this point, intersection point of three wave. And as this incident shock wave move, and this point will move what direction? That direction, right? Exactly similar to the rigid surface. This point will move, zoom in that direction. So if I say C1 is the velocity, wave velocity due to the incident. So another C2 is wave velocity due to the reflected, and C3 is wave velocity due to the wave in the air. And at that point, C1, C2, C3, they have to be all same. So C1, first without before writing, C1, C naught over sine alpha. C2 is C naught over sine alpha prime. C3 is equal to, Willis, what? CG over sine alpha double prime. That's what the general, the Snell's law is. That's about it. Then apply into shock problems. Then that's what it is. C naught over sine alpha, C naught sine alpha prime, CG sine alpha double. This alpha is the same. Where did you get that? For normal acoustic velocity in one media to the other is the same, right at the intersection point. So you have C naught over sine alpha is equal to CG over sine alpha double prime. This is unknown. This is known. It's a given. So, as a result, sine alpha double prime is equal to C naught alpha double prime is sine alpha. Before you write sine alpha, I'm going to say C naught CG sine alpha. As a result of Snell's law, general Snell's law, application is quite a bit. Okay. So this angle, the alpha double prime, due to the ratio here, this ratio CG over C naught. C naught ratio is roughly what? 4.5. But this guy, 4.5 is C naught. CG is about 4.5. So here, if you write this guy, it's going to be 1 over 4.5. And regardless of this alpha, as you will see using the example problem, alpha double prime is always small. Always small. Less than 10 degrees usually. So always that wave front is shooting toward the vertical directions, okay? Oh, we'll do that. We'll do some example problems there. General Snell's law. That. Then for the always think, visualize in your head. Would you do that? Always visualize it. Take the picture and keep it. Take a picture. So C cosine alpha, can you visualize it? Which is normal component of a fluid particle velocity, right? For incident shock wave. That's going up. And minus y. This is due to the reflection wave is coming down. Negative. This is in water side. And this is in air. Really visualize and take a picture and keep it. This guy is in air. normal component, right at the intersection point, intersection point. This is normal component right at O. UG times cosine alpha double prime. Okay. This has to be, one is in air media, this guy is in water media, net fluid particle velocity. That's it. So, very, very nice. And now then, after you go back to office, then you can take a look at this guy's derivation, but not much. This is what I explained it. I want you to think. Then over here, so this is a three equation set. Where that come from? Three equation set, three wave, incident, reflected, transmitted wave. Okay, consider front, back, front, back, front, back. Back is PG and UG, so you can visualize it, this guy. P is equal to rho CU. This is from what wave? Incident wave. Front and back, right? You can say dynamic pressure or gauge pressure. This is from what wave? Reflected wave. This is from transmitted wave. And from 3, you can, I just put that in, you can think, the details part, just expand here. This is the same as that, you can say, but it's really no difference. This ratio is about 3600.